Okay, so let's see. It's 8:05. Usually I get started at 8:05, whether or not people have shown up. It's usually enough time to get most of us here. So I guess one big piece of news is that Jeremy Howard's book is now it has been in stock at Amazon for the last couple of days, and I had pre-ordered a copy and I just got it yesterday. So this is the book. It's called Deep Learning for Coders with FastIron PyTorch, and it's Jeremy Howard's version 2 library course, and it's basically all online in the form of notebooks. So in a sense, you don't have to buy it because it's available free online, but it's just much more convenient to have it in a text form so that you can refer to it and so on. So just so as you were aware of that. And also the course itself, the course 1 version 4 is about to be released online. I believe it is, let me see now. It's released on Thursday the 20th. So at that point, all the videos and all the notebooks, the version 1 course is now public. So that's some interesting news. All right, so let's get to lecture 11. So what's been happening in this class is that up till now, the lectures have been fairly straightforward, and you can follow them without reading a lot of papers. All of a sudden, chapter 11 is different. There are more than a dozen papers referred to in chapter 11, and honestly, there's, you can imagine putting yourself in the shoes of a Stanford student. They have to meet twice a week. So lecture 11 is only one of the lectures they have to cover in a given week. So they get the lecture for chapter 11. Then they have like 2 or 3 days to read the lecture, to familiarize with all the material in the lecture, at the same time as they're doing homework for this class, because they're working on that assignment 5. At the same time, they're working on getting their project proposal ready. And at the same time, they're working on the 3 or 4 other classes that they're taking at the same time at Stanford. So, I don't know how they do it, really. But what I've found is you go through the lecture and you just get overwhelmed with all the references he's throwing out. And I at first thought, oh, you have to follow up every paper and read it and understand it and all that. And then finally, I realized that that's not what he's doing in these lectures. And for example, in this lecture, he's basically throwing in front of your eyes a whole bunch of new techniques, not so that you'll master every one of them, but so that you'll be aware of them, at least in some way. And then if the ones you're interested in, you can follow up on by looking at the papers. And what I kind of got from this, or my take on this lecture 11, is that he wants us to read 2 of the papers, and that is the one by Yoon Kim, which is, let's see, this one. Can you see this one? It's going to take a little while to come into focus. Yeah. The reason why my computer is slow is because I have I must have at least 100 windows open at this point. But anyway, so can everybody see this? Convolutional neural networks for sentence classification? Yep. Yeah, so this is one of the papers he wants us to read. And the other one is this one by Kalkbrenner, the Convolutional Neural Network for Modeling Sentences. So I thought I would take a look at these papers in more detail. I actually have read the Kim paper thoroughly, but I haven't really read the Kalkbrenner paper thoroughly, but maybe we can just go through it and try to pick up the main ideas. The other thing I did was I basically scarfed up every single paper that he referred to, and it's in this, and I've opened it up in Acrobat so that we can actually go through and look at some of the papers. I'll just take you through them quickly now, and then maybe we can look at them in a little more detail. But I mean, my take on this chapter is we're not meant to read every one of these papers, only maybe the first 2. So so this is convolutional networks for sentence classification. This is the original dropout paper, which is really important. And it's something that you can either read, or you can basically look at this diagram. Tells you everything you need to know about what's going on, right? You've probably seen this diagram before. So dropout is just within a layer, you just wipe out nodes at random with some probability. Every node gets randomly. You draw a Bernoulli random variable. That means that something that's either 0 or 1 with some preset probability. So a lot of times they're just using probability of 0.5. So that means that for every node in every layer, you draw this Bernoulli random variable that's either 1 or 0 with probability 0.5. And then if it's 0, then if it's 1, you keep the node. If it's 0, you strike the node and don't use it in the forward and backward propagation. And then at test time, you use all the nodes. So so you're going to end up getting weights just like you would from a normal feed forward neural network, except each layer is only going to have p times a fraction of p the weights that it would normally have if it was full, right? So like here, the probability is 0.5. So on the first level, you dropped 2 of them, 2 of the 5. On the second layer, you dropped 3 of the 5, and on the third layer, you dropped 2 of the 5. This is just from drawing those Bernoulli random variables. So the weights, the other weights are set to 0, and so the average weight is reduced by 0.5. And so you have to do the same thing when you have to reduce the weights by this factor of p, which in this case is 0.5, when you run through the predictions. That's the only. Okay, so next paper is Deep Unordered Composition Rival Syntactic Methods for Text Classification. This is called, he names it something else. He refers to it as the something or other paper, and I don't, I maybe could look it up, but let me see if I can find it. Okay, so we've gone through in this presentation, in the PowerPoint presentation for this thing, we've gone through probably about half of it. And so now I'm going to try to take us through the rest of it bit by bit. So I'm going back to, there's 2 things here. One is the PowerPoint presentation. For every lecture, there's always a PowerPoint presentation. And then there's also a set of notes. And a lot of times the notes are a lot more detailed than the PowerPoint presentation. But in this case, the notes are a lot less detailed. They're just a few small notes on this lecture. So one thing we can do is go through these notes a little bit. But first, I was in the process of showing you all the papers that are being referred to. Let's see, we saw, sorry, let's see, where were we? Yeah, this is Yoon Kim's paper. This is the sensitivity analysis. This is the dropout. Oh, damn it, honey, close the door. Okay, this is the dropout paper. This is the, I can't remember the name of this paper. He refers to it. This is a famous paper by Kai-Ming He on it has a lot of things in it actually, but it's mainly introducing the concept of skip connections for deep residual networks that allow you to go deeper. And that is where you remember what a skip connection is. It's where you go through some layer and you get to the end of the layer and you have an output, but then you remember the input to that layer and you concatenate them together or add them together, in this case add them together at the end. And it's a way of not losing what you had to start with, keeping the initial values of the weights as well as the altered values of the weights. So this is turns out to be a famous paper. Then there's this highway networks paper, which I should go into this PowerPoint to show you what he talks about it. Let's see. Yeah, here. So this is kind of a variant on the residual block. The residual block is what we just talked about with the paper, and this is some sort of fancy version of the residual block where you not only add the original function, but you add some function of it. So it gives you more flexibility in this. It's a more complicated version. Going on. Okay, we saw this paper. This is the residual network paper. This is the highway network paper that we just looked at. This is a batch normalization paper. Again, this is a famous neural network paper. He's basically showing you all the tricks, all the tricks that people can use to make their networks work better. Batch normalization, basically, this is probably what you've seen before, is that you just go to the algorithm. You take the mean for each mini batch, you take the mean and the standard deviation. You normalize it, as we've seen, by subtracting the mean and dividing by the standard deviation for that batch. And that gives you the normalized, which sometimes is called the z-score. And then you go the next step, you scale and shift it with these two parameters, gamma and beta. So gamma is a scale factor and beta is an offset. That's the shift. And this gamma and beta are also solved for as parameters in the neural network. And this turns out to work really well for making sure that the weights don't run away with don't run away to infinity or get cut down to 0. So this is a really important innovation in neural networks. All these things were in the last 5 or most of these papers are probably within the last 5 or 6 years. Some of them go back to 2011, I think.
Question, Joseph. Could you go down a bit on this paper with regard to the normalizing? Normalizing, yes. What is the input get normalized or the weights gets normalized?
The weights.
Okay, and then you further, like, you have then what is scale and shift then?
These are two parameters that make some kind of an adjustment. So it turns out that normalizing it like this, which is what we usually do to inputs in some way, but it turns out they found that this doesn't prevent runaway gradients or vanishing gradients. But when they do this, when they scale and shift, in other words, the next operation here is you multiply it by a scale factor that gets determined by the network, and then you add a shift offset that also gets determined by the network.
Right to the activation.
These are extra weights.
Activations are the one getting normalized, Joseph, I think.
Yes, I think you're correct. Yes. So these are the output from a given layer after it's been processed with the linear layer and the ReLU or whatever activation function that's the output of a layer, and that output becomes, as was just mentioned, that output is activations, right? It's after processing with the activation function, and it becomes the input to the next layer. But before providing it as the input to the next layer, you do all this stuff to it, right?
So X is the input to the next layer, which will get normalized.
Actually, X is the output from the previous layer after the activation function has been applied.
Correct.
That's what was just noted. Yeah.
Which will get normalized and input to the next layer.
Yes. So X gets normalized first, and then scaled and shifted. and then that becomes the input to the next layer.
Okay, scale. So normalize is we used to do that. The value need to be between the 0 and 1.
Yes. Well, no. This isn't. This is different. This is a standard. No, this is standardization. So it's not between 0 and 1. You're subtracting the mean, so that and then you're dividing by the standard deviation. So it can have, the x's can have values anywhere from, well, the input x's are between 0 and, because they've had the ReLU activation applied, they're positive. So the input xi's are positive. But then after this, they're converted into, they're not between, normalizing doesn't put them between 0 and 1, right?
So excuse me, can I just intervene? So this is called standardization. And what will happen is that the values will be centered around 0. And usually the maximum values that you'll find will be in terms of sigma, 3 sigma,
That's right.
4 sigma.
That's right. So you're actually subtracting the mean to make it as, I forget the man's name who just spoke. Yeah, when you subtract the mean, sorry,
Abhijit.
Abhijit, thank you, Abhijit. So absolutely right. When you subtract the mean, that means that the distribution is now centered on 0, right? So and the other thing is you're dividing by the standard deviation. So you're basically converting the x's to units of standard deviation. So, you know, and they can have any values from 0 to infinity, of course, but they're more likely to be between 0 and 3. You know, they're not likely to be large. So you're not compressing them between 0 and 1, but you are compressing them, say, between
3 standard deviation. And
yeah, 3. Yeah, you're not likely to get something more than 3 standard deviations if it's a Gaussian. But if it's not a Gaussian, you know, you can have larger values. But it's not. But just to correct the, it's not between 0 and 1, because this is called standardization. It doesn't. It's not the same. It's not the same processing that gives you between 0 and 1.
Okay, so on the next stage, we are scaling and shifting. Are we scaling and shifting y, or now we are scaling and shifting x again?
No, the arrow goes to the left. So you start with the x's. Okay, each process, first you compute the mean from the inputs, right? Then, and these inputs, as was mentioned, are activations. They're after the activation function has been applied. So the first thing is you calculate the mean.
Yeah.
Now that you've got the mean, you can calculate the standard deviation, which really this is the variance. You know, you're calculating the variance. Then you take the square root of the variance, which is the standard deviation, and then you process it this way: x minus the mean divided by this square root of the variance plus some small number. This is for stabilization, for to keep it well conditioned. So this epsilon is just some arbitrary, very small number. Okay, so now you've got the standardized values.
Yeah.
You started with the xi's, now you've got the x hat i's. Then you scale them and add an offset, and then you have the y i's. And then this becomes the input into the next layer. And the key thing is that these parameters are part of what's learned by the network. So they're along with, they get learned along with the weights by the process of backpropagation.
Right. So this scale and shift is a new step, which is a part of batch normalization.
Correct.
Which is helping to stabilize the network, or what?
It solves the problem of exploding gradients and vanishing gradients.
Okay. Yeah. Because that's what we have been doing up to the normalize. So I think this is the scale and shift is the new step.
That's right. And that's what makes this batch normalization. That's what makes batch normalization. Basically, that's the key step in batch normalization. So, you know, if you know nothing about the paper, without reading all this paper, see, every one of these papers is very nice. It's like 10 pages or something. But since there are like 15 papers, you know, that's a lot of reading if you had to read everything. So the best thing to do when you go through these papers is just to pick up the things that's the main things, you know, as you look at them. And, you don't have time to read everything. So you just try to pick up the main ideas. So that's the main idea from that paper.
Yeah.
Then this paper, Network in Network, this is about one-dimensional convolutions. And so he talks, but this isn't, to tell you the truth, I did not understand this paper very well. He talks about doing convolutions, and then in between them you have, he calls it an MLP, which is multi-layer perceptron, but that's just another word for a fully connected neural network. In this case, there are 2 layers. And he's somehow is equating this to 1-by-1 convolutions. And let's see. So this is MLP, that's a multi-layer perceptron. And multi-layer perceptrons with a ReLU activation function, you can sort of recognize that. This is the linear layer, you know, weight times input plus bias vector. Max of that and 0, that's just the ReLU layer, right? That's just the ReLU activation. So this is the output of a ReLU layer. And so this is layer 1, and there can be n layers, so each one of them has its own weight matrix. So n is the number of layers in the perceptron. Rectified linear unit, that's ReLU, is used as the activation function, that's here. Okay. So this is some kind of a cascade of these things ending in a fully connected layer that maybe ends in some kind of a classifier, you know, with a softmax or something. Let's see, global average. In this paper, so NIN is network in network, which is supposed to be, I mean, he basically says this is the same as this is a 1-by-1 convolution. And then he just talks about the experiments that he's done and how well he's done. I'm not going to go in more detail about this. These are all standard data sets that they use. And then this is the feature map, visualization of the feature maps that you've seen before. I guess this is a classifier that is trying to look at images and tell you what's in them. So it's a sort of a hybrid of an image and neural network and NLP model. So you have several classes of things that can be in the image, and then you're supposed to be able to predict what's in the image. What else do we have here? I don't see what an NIN is beyond, I mean, I can understand this architecture, but I don't understand why they say, okay, I guess this is it right here. So you have an image, and then you do some convolutions, and then you put that through a fully connected network, and then you end up, and each point gets mapped that way. And he's sort of comparing that to a linear layer that can do the same thing. MLP conv layer includes a micro network, that's this fully connected network. Both layers map the local receptive field to a confidence value of latent concept. I'm not sure what that means, but the point is that using 1-by-1 convolutional network allows you to take linear combinations of the input. I think, to me, that's what the 1-by-1 CNN does. It allows you to take linear combinations of the network and of the input and add them together. Let's see. So that's network and network. Recurrent continuous trends. This is another paper that he talks about. Let's see. We can refer back to, in each case, maybe we should refer back to the original notes to see what he says about these papers. So here's what he says about 1-by-1 convolutions, and this is the paper that I got that we just looked at. 1-by-1 convolutions, aka network and network, are convolutional kernels with kernel size 1. To tell you the truth, I did not get that out of this network and network paper. I didn't see anywhere where he was talking about 1-by-1 convolutions. map from many channels to fewer channels. Yeah, so a one-by-one convolution, what is it? It's basically a constant, but you usually have a whole vector of constants. And so each constant, you basically take a linear combination of the input with each of those, adding multiples of that input together. Okay, maybe we can find an example of a good example of that to refer to, but and the advantage, I guess, is that instead of using a fully connected layer where you have to add a lot of parameters, you're only adding a vector of parameters instead of a matrix of parameters. A one-by-one convolution is basically a vector of parameters that have to be solved for, whereas a fully connected layer, you have to solve for weight matrices and so on, which is a lot more things to solve for. Okay. So this is the Kalkbrenner and Blunsum paper that I just looked at. We'll go back to it. First successful neural machine translation efforts uses a CNN for the encoding part. So that would be, I guess this is the encoder using a CNN, and then an RNN for the decoder. And we've looked at RNNs before. So this is sort of familiar to you. This is the hidden layer of the RNN getting passed from one to the next. Each one of these units is for one of the words in a sentence. And then, let's see, this is the initial, let's see, I'm not sure what, oh, okay. And this is the word coming in. This is each word of the sentence coming in. So you have to map this in your mind to what you've normally seen as the architecture of an RNN. Remember, there's the input is usually shown from the bottom. I guess this is the bottom if you go from left to right. The word comes in. This is the first word in the sentence, the second word in the sentence, the third word, and the output is two ways. You get the hidden layer all by itself that you could actually skim off of that, and the same thing gets passed to the next layer. So these two arrows are the hidden layer from the first word. And then these two layers are the hidden layer from the second word, and so on. So this is the architecture of the Kalkbrenner and Blunsum paper. Now we can go back to that paper and look at it a little bit here. So let's just see if anything strikes our fancy as we look through this paper. Okay, so there's this is the schematic for the RNN that we just looked at. This just means it's repeating, so you basically unroll it to make it look like this, all right? The input word, the output is the hidden state, and the output also goes into the next layer. Okay, what else can we see here? Current language model, it looks like a softmax to me, so you recognize that. This must be the CNN. CSM, it's an abbreviation for something in this paper, but I'm pretty sure it's the CNN. It's the CNN layer. So here's an input sentence: the cat sat on the mat. You are looking at the words in pairs. And so there's a couple of layers here, I guess. This is a filter of length 2, and then this is a filter. So it maps each two words to a number, and then there's another layer where you have a filter of length 3. So each the filter gets applied to 3 words at a time, or 3 of these latent states at a time, and gives you one output. 3, the next set of 3, and the next set of 3. So these 5 inputs give you 3 outputs, and then let's see, this must be a linear layer to get the last output. Let's see. or the encoding is the output for the encoder. So so it must be, L3 is a top, K2, K3 are weight matrices. L3 is a top weight matrix. To the right, an instance, one-dimensional convolution between some weight matrix, Ki, and a generic matrix. Yeah, so I think there's convolution layers on top of that. So I think the thing to keep in mind from this paper, or just to take away from it, is that it's a translation model where the encoder is a CNN and the decoder is an RNN. And let's see. So then they're looking at some different possible architectures. I'm not sure I get this. So this is, okay, so this is the output of the encoder, and then there's a bunch of, these are fully connected layers, the arrows it says. The lines are columns of weight matrices. So this gets mapped into the RNNs, which do the translation. Not much more to get out of this. And they talk about some experiments they've done. English-French translation. Okay, I don't think we need to look at this anymore. The next paper he refers to is this Santos paper about character level representations for an important problem in NLP called part of speech tagging. So you're trying to get, it's kind of like the equivalent of a segmentation model where each pixel has to get classified in an image problem. Each pixel has to get classified. In this case, each word has to get classified as a part of speech, whether it's a noun or a verb or whatever. So that's what the POS tagging problem is. And let's see what he says about this in the notes. Character level. So he's doing convolution over, so this is a little different. It's doing convolution over characters to get word embeddings. And then a fixed window of word embeddings is used for part of speech tagging. So here are the input letters. This is a linear layer over those. I guess this, these little things must mean that the convolutions. And then the outputs are the encodings. And then, so then once you have the encodings, then you map them, then you take maximum pooling and you get your final output. I don't know what this CLU is. Convolution over, okay, so then, and this is the next, so that's this paper. So now let's look at this Santos paper in a little more detail. This is that paper we were just looking at. And this is that diagram. So he's basically chopping out the main ideas of each paper and throwing them in front of you. Almost every slide has a new paper with a new main idea on it to look at. So I guess the first thing, the lowest level thing you can get out of this diagram is that now we're doing something that we used to do with words. Now we're doing it with characters, and we're getting character level embeddings. And these are going to help us get part of speech tagging. So he does word level embeddings and character level embeddings. Training, I mean, all this stuff is not worth looking at right now. And then he just, all of these papers always have, okay, now we're going to do an experiment and show how we're now state of the art in this or that. Okay, I don't get much more out of that. Okay, it's interesting how Manning's name, our instructors, his name pops up all over the place in these papers because he's really intimately involved in this, in all of these NLP problems. A lot of these papers were written by him and his students. Back to the presentation. So the next thing he talks about, we just, wait, what did we do? Character level representations for part of speech. That's the one we just went over. The next one is character aware neural language models. Character-based word embedding. So again, it's character level. It utilizes convolution, which we've talked about, highway network, which we've talked about a little bit, and LSTMs, which we've already talked about before. So here's an example of the architecture. Here's the input sentence. These are the encodings of the words. So absurdity is encoded. It's, normally remember the encodings would be like of length 300. There would be a vector of length 300. This is just a schematic to show, 4 instead of 300. Then convolution layer with filters of different widths. So here's a filter of width 3. That's going to give the yellow. A filter of another filter of width. A filter of. Why do we have? Okay. So this is a filter of width 3. You can see that it's combing over the inputs and it's combining 3 inputs to make 1. This one is a filter of length 2. It's combining 2 inputs to make 1. And this is a filter of length 4. It's combining 4 inputs to make 1. So let's see, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 inputs. I guess they haven't shown all the words. The 9 inputs in this case go to 1, 2, 3, 4, 5, 6, 7 outputs. And that's because we're just, if you slide this convolution over, over the 9 words, you get, okay, if the word is if the sentence is of length n and the filter is of length m, then you get n minus m plus 1 results from the convolution filter. And that's because there's a limit. You can imagine sliding this thing from left to right. There's only going to be, there's 9 words, there's only going to be 7 positions, 9 minus 3 plus 1. So this is one position. If you slide it 1 unit to the right, that will give rise to this column. The next one will give rise to the 3rd column, and so on. There's going to be 7 columns. I don't understand how this gets 3, how this has a length of 3, whereas this one has a length of 5, because I think that, this is the dimension of the encoding, and that should be the same in all of these, as far as I know. So I'm not sure why this blue one isn't also of length 4, and the red one isn't also of length 4. But in any case, that doesn't matter, because the next step is max pooling, where you just, let's see, why? Yeah, max pooling, you just take the maximum in each column, and then that maps to here. So this column maps to, oh, no, I'm wrong. Okay, they basically took this column and flipped it on its side, took this column and flipped it on its side, and took this column and flipped it on its side. So something else must be going on to get this convolution of multiple layers. We see that there's multiple layers, the yellow, the blue, and the red, and that the layers have different widths. That's shown because here's one with the convolution of width 3, a convolution of width 2, and a convolution of width 4. So why does the output of this have okay, so each row in this case is, you take the maximum of it and it maps to one of these squares. That's the max pooling. And same here. So there's 4 rows. You just take the maximum in each row and map it to that spot. The maximum of the 2nd row gets mapped there. The maximum of the 3rd row gets mapped there, and so on. And the same process happens with this blue matrix. So you take the max pool, you stack them end to end. Then there's another Max over time. Okay, so this is the max pooling layer that we talked about. This is the highway network that maps this thing with some function, but then it adds the original back to itself. And then it goes into an LSTM. The architecture of an LSTM is similar to an RNN, except that there's a hidden layer and a memory cell as well. And then there's a softmax to get the distribution over the next word, and then you predict the next word. So this is a language model that takes an input string of words and predicts the next word. So this would be the one that we want to predict the next word from, absurdity, and then it predicts the next word from its LSTM. So this is similar to what we saw before from the paper where there was the encoding was done with CNNs and the decoding was done with RNNs. This is the same similar paper, except it's done with character level instead of word level embedding. All right. Okay, the next page is this paper. Let's see. Let's see. So LSTMs dominant, CNNs attention, but all the models are not deep, not like the deep models in vision. So then these guys said, okay, what happens if you build a deeper network for an NLP problem? And it also works from the character level. So let's have a look at this paper really quickly. That's that one, that one. Sorry. Yeah, so this is that paper, very deep convolutional networks for text classification. And then it's one of the authors, as you can see, they're all Facebook, most of them are Facebook people, and this is a very famous guy, Jan LeCun. He's one of the guys that got the Turing Prize last year, I think, one of the 4. So let's see, what do we have here? Okay, so just having a look at this architecture, very deep convolutional neural network. Okay, lookup table, convolutional layer, convolutional block, which this would be the length of the filter. So it's a length 3 filter, and it's there's 64 filters. Optional shortcut. Remember the you know, the highway network where you can add the some function of the original input back to the output of each block. So you got all these blocks. Then you do some kind of pooling, more convolutional blocks with optional shortcuts. So it's like, oh, and here the dimensions are changed. You're doubling the number of filters. And here you're doubling again. So just notice that there are blocks that involve shortcuts. So there's a bunch of blocks followed by pooling, a bunch of blocks followed by pooling, a bunch of blocks followed by pooling, and each time the number of filters changes. So first we start with 64 filters, and then 128, and then 256. And when I say filters, I mean you know, these convolutional neural network filters of length 3. Another bunch of blocks. Okay, and this is not max pooling, this is pooling over 2. So it basically means you're averaging every 2 neighboring weights together. So it basically, you've doubled the number of filters, but then you get back to the same number of weights by the pooling layer. That's what these. So you basically if you look at the output, it's 128 by s over 2, where s is the length of I believe s is the length of the sentence, or the length of the sentence in this case in characters. So notice that this output is 64 times s. This output is 128 times s over 2 because of the average pooling. So it's the same size output. Then average pooling, but now, okay, but so now the output goes into this one and comes out and then gets averaged again. And so each time you get the same number of outputs, because it's still 64 times S. And again, the same thing by average pooling, 512 by S over 8, it's still the same number of outputs. So you're maintaining by these blocks followed by pooling layers, you're maintaining the same size. I guess that keeps the problem simpler. Then you do max pooling, well, K-max pooling. Remember, the difference between max pooling and K-max pooling is that K-max pooling looks for the K-maximum values and keeps them. So K could be 2, or it could be 3, or in this case, it's K equals 8. So now your output is 512 by K, and then you have some fully connected layers followed by ReLUs, and then you have the classification layer. So it's just an architecture to look at. And then, let's see, he looks at the insides of some of the layers. There's a batch norm and a ReLU, which we've already seen about. And then he talks about his results. So basically, I think that's all we wanted to see, what the architecture looks like. I think that's what the point of this lecture is to throw at you all these different architectures. And here, and in some cases, he actually goes into some detail. I noticed that, let's see, where's my notes? Yeah, like slides 20 through 26 all concentrate on the Kim paper. We'll go back and actually look at the Kim paper. And then slide 29 and even slide 30 and 31 are also focusing on the Kim paper. So that's the one we really want to look at closely. Let's see. There's more, let's see. Slide 35 is where he introduces the Jan LeCun paper. Sorry, what? I got the wrong, oh yeah, this, well, that's the network in network, I'm sorry. We went through Connell, Schwenk, LeCun, and Barl. That's the paper we just looked at. And then he has a couple of more slides about, we've already seen this. So basically he's done the same thing that I did when I went through it. It's just to focus on the architecture and just sort of describe it. And in each case, they're doing things to each block that the average pooling, you inflate the number of channels, but then you deflate it back after each one of these blocks to get back to the same size you started with. Although, you know, it's organized differently, and the array size is different, but the total number of elements in the array is the same. That's the point, right? So from here, from the output of this first layer, your output is 64 by S, where S is the number of characters in the sentence. And then it maintains that although the array changes, the number of rows and number of columns changes, but the total number of elements in the array is the same all the way through until you get to this max pooling. And now you're starting to condense it down. Excuse me. And then you have these fully connected layers. Actually, and so 8 times 512 is 4098, right? 4096, sorry. So the input to this one is 4096. The input to this fully connected layer is 4096, and the output is 2048, then followed by a ReLU. The input is 2048, and the output is 2048, followed by a ReLU. And finally, you have 2048, a 2048 layer getting mapped to however many classes you're trying to classify. So in that sense, this architecture makes sense. The details are probably a little bit fuzzy, but we understand each piece now. We understand what convolutional blocks are. We understand what average pooling is. we understand what these shortcuts are, and we understand K-max pooling, and we understand linear layers and ReLUs. So basically, you should think of these things as kind of like Lego blocks that people put together to build networks. How the engineering knowledge comes into play as to how to structure these things, that's something we don't have right now. We don't know how to think that way, but the researchers do this. They have ideas, they come up with architectures, they try them, they find architectures that work, and they usually have ideas behind why they choose one architecture or the other. That part we're not covering here. We're just sort of showing you what the architecture looks like, what the architecture that these researchers found after months and months of work, they found it to be effective, and then we're seeing it. So that's this VDCNN. And this is kind of a smaller version of the schematic. So there's two, I guess the halving, we saw that. The halving means to cut in half. When local pooling, we saw that with a local pooling size of 2. So each 2 elements get condensed into 1 by just averaging them or taking them. I think when in local pooling, they just take the average. Let's see, here's the experiments. A bunch of different experiments. Again, we don't know what all these experiments are, but Yelp reviews, polarity means plus or minus. It's basically sentiment analysis with 2 classes. Yelp review full, there's 5 different classes. So really good, really bad, and some classes in between. So instead of having just a two-way classifier, you have a 5-way classifier. Yahoo Answers is topic classification, and there are 10 classes. So that's another common problem where you want to look at some text and decide what topic it belongs to. Amazon reviews full, again, there's 5 classes. In Amazon, they allow you to rate things with five levels, right? But then you can also condense it and just, what you would do if you want to do sentiment analysis is you would take out the middle layers and just have the top, or maybe you could take 4 and 5 and condense that together to make a plus, and 1 and 2 and condense that together to make a minus, and then a rating of 3, you would just either eliminate those reviews or randomly set them to pluses or minuses. I think it's better to eliminate them. Eliminate the reviews that got a 3 from your data set. Let's see. So that's the experiments. And there are some more. And these are just experiments that he's done with different depths, ranging from 9 to 29, and finding, in this case, they found really great results with this very deep network. So now they're basically trying to extend the advances in image processing in computer vision to NLP, and they're finding that it works well. The same concepts from computer vision work well also in NLP. Okay, the last couple slides. Rnns are slow. We've seen that. They parallelize badly because, you know, you've seen what the RNN looks like. You have to go through each of those fully connected networks in series with the hidden layers and so on. So take the best and parallelizable parts of RNNs and CNNs, and then that's the concept of the quasi-recurrent neural network. And so we have that paper here too. Let's see, where were we? This is, okay, this is the deep network. So this must be I arranged these in order. So in order that they were referenced. So here's the quasi-recurrent neural network paper. It's from 2016, more recent. These people are all at Salesforce, which is kind of interesting. Now, firms, well, of course, we knew that Facebook and Google and Amazon all have very strong research arms, but here now this Salesforce company, which I don't know what their actual business model is, but apparently they have a really strong research arm too. And they invented this quasi-recurrent neural network. And let's see, so here's sort of the schematic, what it looks like. LSTM linear, okay. LSTM, linear LSTM. So this is kind of like a 2-layer deep LSTM kind of a thing. This is a CNN followed by max pool, 2 layers, and then a QRNN. So first layer is a convolution. I don't know what FO pool means. Red signifies. So red is matrix multiplications, convolutions or matrix multiplications. The blue is parameterless functions like averaging, like pooling and stuff. There's no parameters involved. Operating LCMs can be factored into red blocks and blue blocks. Okay, I don't really understand this. I don't really understand what a QRNN does. They give you all the familiar looking equations. You know, this would be like an activation function of some sort. This is like a linear layer, and they're leaving out bias. So these are maybe, not sure what they are, what the Z, F, and O are, but we can recognize them as linear layers, though. And then this is a gate, some kind of a gated architecture. So this must be a modification of the LSTM. Anyway, it's not necessary to go into the details unless one is interested. They introduce some concept of attention. Anyway, the details are a little involved. So I'm not sure what we're meant to get out of that reference. Back to here.
I think,
yeah.
Joseph, the idea is to point in the direction of transformers or the desire for parallelization. So LSTM doesn't let you do that at all. It's totally sequential. CNNs have an element of parallelization in the sense of them being able to operate as filters over small subsets. In the case of images, it's obvious, but in this case, they use the example of characters, for example, that you have convolution windows over. And then the quasi-RNN is an attempt to apply parallelization with the details in the paper of bringing in convolution to help with making some parts of the LSTM somewhat parallel. But that's why it's a quasi-RNN and not a full sequential RNN. And you know, obviously you'll need to go through the details in order to figure out to what extent they've succeeded in parallelizing or bringing in concepts of parallelization. But this whole direction obviously becomes kind of moot once you go through, as he gets to in the next couple of slides, as we head towards transformers. It takes the whole thing, whole RNN concept, and blows it apart by just parallelizing the entire sequence that you have.
Yeah, and so you can, I guess that's a really good overview, because you can see that CNN does, it eliminates having to go through, you know, a fully connected network for every word in the sentence. It combines words or characters, so it slides this window over the sentence, and then instead of having to process every single word with one of these fully connected networks, you only have to process the, you know, you group, you apply this 3, in this case a filter of length 3, and then you have 1/3 less things to process, you know, because in some sense. And QRNNs, I guess QRNNs, I guess the thing is that you take advantage of this partial parallelization of the convolution to make less work for the, and even pooling, to make less work for the RNNs to do. Yeah, so it's something in between. But right, I think that when we learn about transformers, all of this stuff, and attention and transformers, all this stuff becomes old hat and not necessary anymore. And the interesting thing is, I think that's what this lesson is showing us, that guys like Manning, who spent their whole lives learning all of these fancy rules about how languages work and so on, and then you have these guys like Yoon Kim come in with his paper, and he says, I can do all the stuff you guys can do, and I don't know anything. I don't have to know anything about linguistics, and we'll see that. And the interesting thing is that Manning takes that all in stride. You know, he's both a classical linguist guy, but he's also in the forefront of using neural networks to get results for language models. Let's see, here they talk a little bit more about the QRNNs. And the main advantage seems to be that QRNNs are much faster. They have less processing from RNNs. Okay, so here's the LSTM, which has lots and lots of serial processing. That takes a lot of time. LSTMs on GPU, you can speed it up somewhat. Looks like a factor of 2. And then a QRNN speeds that up. I mean, you have this overhead from softmax and optimization. And now the serial part from the LSTM or from the RNNs becomes only a small contribution instead of the major contribution to the time. So that, I guess that's the takeaway from the QRNN, is that it's a way of making of getting similar results but much faster. Similar results as LSTMs but much faster. Yeah. And what is this batch size? So these are batch sizes versus sequence length. I guess the thing, so this is a speed up. I guess this is a speed up time as a function of batch size and sequence length. And so it looks like you get only a little speed up when you have large batch sizes, but smaller batch sizes you get significant speed up. I guess that's the takeaway from this part of the slide. And these are the scores on, it doesn't say here what the test was, what the model that they're testing was, but if we look at LSTM, QRNN plus zone out, I'm not sure what that is, roughly the same number of parameters. Better, I guess in this case, the scores, lower scores are better, so QRNNs are doing better than LSTMs. Lower scores are better. LSTM, okay, so this is the models from this paper, and they get scores between 78 and 82. Previous, so they're saying that the QRNN actually outperforms the LSTM, and at least it performs equivalently or better than the LSTM, and it's much faster. So that's the takeaway for QRNNs. Better and faster, and they're using, I guess they're doing a sentiment analysis task, which means, you know, classifying a review as positive or negative. Let's see, their models, time and accuracy. So, I mean, the takeaway from this slide is that their models are almost as accurate as the other state of the arts, but they're much faster. So there's a trade-off there. Okay, limitations. Doesn't work well as well as LSTMs for character level language models. It has trouble modeling longer dependencies. When they say longer dependency, they mean in a long sentence, capturing relationships between, you know, words that are at the beginning of the sentence and words that are at the end of the sentence. That's always the problem with these sequential models. It's hard to capture all the relationships in a long sentence. Still faster, often need a deeper network to get as good performance as LSTMs. And so the trade-off is that I guess to get the same performance as an LSTM, they have to go deeper, but he says here that even when they're deeper, they're still faster because we saw the tremendous speed increase. Effectively, they use depth as a substitute for true recurrence. Okay, so it's basically a improvement on LSTMs in some way. And then this is the last slide. Even with the improvements of GRUs and LSTMs that we saw were better than RNNs, we still get even better performance when we have an attention mechanism to deal with the long-range dependencies. So that long-range dependencies is the big problem in all of these variations of RNNs, LSTMs, GRUs, and even, I guess, CNNs as well. And so this is sort of priming us for the next, I think the lecture, not the lecture after next week, but the lecture after that one when we start talking about attention. And then as Srinivas says, attention allows us to throw away the serial nature of these language models and speeds things up and just opened up a whole new world for language for all NLP problems. And that just happened, I think in 2015, I think, were the first attention papers, but the first large-scale systems like that use attention and transformers came out just in the last, what, 3 years or so. Okay, so I took us through the whole, basically the whole lecture, trying to pay attention to all the many things that he brings up. But now we're going to drill a little deeper and go back to the two papers that he really liked to, that he really recommended. And that is this Yoon Kim paper. And then there was another paper, which I'm not going to go into as much, but I do want to go into this Yoon Kim paper. The second paper that he recommended reading was this one, not this one, sorry. I've lost it. It must be, excuse me, I must have lost that second paper that I wanted to look at. But I'm basically going to look at this Yoon Kim paper because that's really the main paper that he talks a lot about in this lecture. So, and this is a remarkably easy paper to read. It's only 6 pages, of which only really 4 pages are talking about technical details. Just going to quickly scroll down to show you. And then the last couple pages are just comparing their model results and discussions. So it's a really nice paper to read if you haven't read a lot of papers before. And so let's have a look at these. Let's have a look at this paper. So this is the guy who sort of came in 2014 and said, I don't have to know anything about linguistics or classical NLP, and I can use CNNs to give me, to build a model really simple to understand for almost anyone to understand that gets results just as good as all of you guys in the big leagues. And he has a really simple architecture. Also, I like this is a really well-written paper. There's a lot of nice phrases in here that I noticed. One of them is that he says that word vectors, remember the word embeddings that we've talked about? Word2Vec, for example, and Glove, that give you these word embeddings. He says that word vectors wherein words are projected from a sparse one of V encoding, that's that one-hot encoding of the V vocabulary. Remember, so the primitive version of a word vector, remember, is just a one-hot encoded vector with a very long length equal to the length of the vocabulary. So maybe you'd have 20,000 words in your vocabulary, and each word is represented by a 1 in the slot where that particular word occurs in the vocabulary. right? It's a one-hot encoded vector. So he says that word vectors are basically these one-hot encodings projected onto a lower dimensional vector space. Remember that lower dimensional vector space is a roughly 300 dimensional vector for, I think, for word2vec and glove, somewhere between 300. I think they use 300 as a standard, but I've seen 500 also. Basically, he says that word vectors are essentially feature extractors that encode semantic features of words in their dimensions. So what does this mean? Semantic features, semantic means meaning. That's what semantic means. Syntax, you often see syntax and semantics used together, and syntax refers to structure. For example, the structure of a sentence in terms of nouns and verbs and so on, and the rules for that structure. That's the field of syntax. Semantics refers to meaning. So what is he saying here? He's saying that these word vectors in some way are encoding the meanings of these words. And remember, we've seen these maps where you have, king is to man as queen is to woman in the embedded spaces. The difference between the queen and the woman, the difference between the queen and king vectors are similar to the difference between the man and woman vectors. So the vectors are certainly encoding some feature that has to do with the meanings of these words. But anyway, I just liked that sentence. It was a nice. If I would highlight it, I would. Yeah. That's the sentence that I was just pointing to. In these dense representations, semantically close words, that means words that are close to each other in meaning, are likewise close in Euclidean or cosine distance in the lower dimensional vector space. And remember, what he means by this lower dimensional vector space is the 300 dimensional word embeddings. So anyway, let's look at the architecture. And somehow, well, I'll get to that later. Okay, so here's the sentence. Here's the words in a sentence. And each word is embedded in a 300 dimensional vector space, which is schematically represented by this 6-element space here, right? I mean, there's no point in having it run all the way across the page 300. So just keep in mind that this is the representation of the sentence where K is the dimensionality of the embeddings, right? So you start out with an input sentence, and these vectors are already known from word2vec. So we have the embeddings from the sentence. But he comes up with this new twist on this. He says, okay, let's start out with not just one copy of the sentence, but 2 copies of the sentence. And the second copy will be, the weights will be, the embedding vectors will be determined by our network. So he starts out with a kind of like a random initialization. And then we can combine them at the end in some way. So he does this, he does his architecture in 3 ways. One is just using the predetermined weight vectors, the predetermined embeddings from word2vec. The second way, he tries to eliminate the pre-known vectors from word2vec and just solve for them as part of the network. And then he has a hybrid approach where he does both. And I think what he does at the end is he concatenates them together, but we can wait and see that. Okay, so the first thing he does is he has a convolutional layer with multiple filter widths and feature maps. We already saw this in another paper. What's a feature map? Well, a feature map is when you run this convolution. Let's say this one here, a length 2 convolution. You run it down the sentence, and for each pair of words, you get an output. So that would map to one output. That would map to the next one. And again, the way we're doing this is so there's n words in the sentence. There's m, the convolution of length m, in this case length 2. So here the sentence is 1, 2, 3, 4, 5, 6, 7, 8, 9. And I guess we're doing some kind of sub-word embedding for the don't. Don't gets divided into 2 words. I'm not sure how they decided that they were going to do that. But in any case, we have, what do we have? 1, 2, 3, 4, 5, 6, 7. There's 9 words in the sentence, or 9 objects in the sentence. The convolution has a length of 2, so how long would the feature map be? Well, you know the formula is n minus m plus 1, which you can easily convince yourself of that's the right formula. So in this case, n equals 9, m equals 2, n minus m plus 1, sorry, is it 9, or is it? Yeah, it's 9. N minus m plus 1 should be 8. I'm not sure why we have 7 here. Okay, so yeah, I'm not sure why we have 7 here. That might be a typo. Here is m equals 3, so 9 minus 3 plus 1 should be 7. I don't think he's showing that quite correctly, but you can convince yourself that if you have a convolution of length 2 running over a sentence of length 9, there are 7 possible positions, right? Here's 1, 2, 3, 4, 5, 6, 7. Oh, there's 8. Wait. N minus m plus 1. There's 8 positions, right? N minus m, 9 minus 2 plus 1. So there's 8 possible positions. So this should have length of 8, and it only has length of 7. That's a typo, I think. You can easily convince yourself, right? There's position number 1 is here. Slide it down 1, 2, so that's 2, 3, 4, 5, 6, 7, 8. And you can't go any further, right? Without going off the edge. So there's 8 positions. With a length 3 convolution, you can have 1, 2, 3, 4, 5, 6, 7, and then you can't go any further, right? So that's 9 minus 3 plus 1 is 7 positions. That's that tells you how many positions, that's the length of your feature map, okay? Right, and the convolution that you're using has to have a length equal to k. So it's a one-dimensional convolution in the sense that we're sliding it in one dimension, but it has in this case 2. It's a length, the filter is of length 2, but it's represented by a 2 by k matrix, where k is the length of the embedding vector, right? So it's a little confusing when you see this. A one-dimensional convolution, you would think would just be a vector of length 2, but no, because it has to apply, because each word isn't represented by just one, each word isn't represented by a scalar, but it's represented by this vector, the word vector, right? So the convolution filter has to have 2 by k elements in it. Does that make sense to everybody? Let me pause here for questions, because I've been talking a lot. Let's see if there's anything in the chat. FastAI D2 folder has batch norm implementation, by the way. Oh, that's great. From Wencheng. Okay, are there any questions up at this point? Okay, so we're basically looking at the architecture of this Yoon Kim paper. So that's the first element, is these the convolution layer, just one convolution layer with several different filters, right? So you could have a filter of length 2, a filter of length 3, another filter of length 2. You could have a filter of length 5 if you want, different lengths. And he doesn't really say here what the filter lengths are, but I think he says later on. And then the next step is max pooling over time. So that means from each one of these feature maps, and I'm calling this a feature map because it's, you see that in the literature all the time. A feature map is the result, is the output of a convolution layer, right? So it's basically mapped these features in this case, groups of words, into another set of features. And so, a feature of length 2 is looking at 2 grams. A feature of length 3 is looking at 3 grams. A convolution of length 2 is looking at 2 grams. A convolution of length 3 is looking at 3 grams. And in this case, notice that there's more than one different convolution filters of length 2. So it's actually looking for different kinds of 2 grams. You can look for different kinds of 2 grams. Like maybe subject verb would be, you might think that it would find a subject verb, or you might think it might find a verb adverb. There's different kinds of 2 grams that occur in literature, and so you might have a whole bunch of different convolutions of length 2 generating a whole bunch of different feature maps, right? And then you have 3 grams generating its own feature map. And then each of these feature maps has different lengths because of the interaction of the convolution length with the sentence length. Gives you a different length for the feature map. In this case, he hasn't bothered with that. Well, he has shown that some of the feature maps are of different lengths than others, but he could have actually taken the trouble to make them the correct lengths. But the point is, these feature maps are all of different lengths, and so you might think, well, how am I going to combine them? Well, the ingenious solution is max pooling, right? You represent each feature map by a single number, which is the max. The max over time means the max over the sentence, right? And so this feature map gets represented by the maximum value. It gets mapped there. See, we have 4 feature maps, and each feature map maps into one of these. So after running this max pool layer, now we have 4. We just have 4 features, and then we can map them with a fully connected network into a classifier, a 2-way classifier if we want. Or we can map them into a 10-way classifier if we want, right? With a linear layer followed by a softmax. So the innovations are A, the convolutional layer with multiple filter widths and feature maps, B, the max pooling, and C, he applied dropout. So these are the things he did that maybe other people before him didn't do. And then the third thing is this, and then how many things did I say? 1, 2, 3 innovations. The fourth innovation is using a hybrid model. He says you can either use predetermined embeddings from powerful language models like Word2Vec embeddings, or you can solve for your own embeddings in the process of solving your neural network. That's always possible. And then the third thing he did is use a hybrid of those. And the interesting thing is, we just learned about skip connections and how you run something through a network and then you add back the original thing so you don't lose it. That's kind of what this is. It's just another form of that sort of archetype of a skip connection. You've got this predetermined fixed embeddings that you're not doing anything with, but then you're also at the same time solving for new embeddings, and then you use both of these by adding them together. I think he takes I think he either concatenates them or averages them. I'm not sure which way he does it in this paper. We'll find out as we go through it. Yeah, so that's basically this whole paper in a nutshell. And let's see, it looks like, yes, someone?
I was trying to make some, well, the graphic, the graph.
Yes.
I was trying to make some sense about why he uses 7 as output and the convolution as we know. But if you see, he used the first layer, the top and the bottom, to construct like the bottom and the top of the output. But he uses the layer behind to construct the other one. And I was thinking of that, why he for the top and bottom uses this, and for the middle part that. And if you try like take the top and the bottom and construct that, the other 5 in between can come from the back. If you do the normal convolution, but stopping, well, you only get 5 from behind, because, for example, I am not so sure, but the yellow one that has 3, you have 9. But if you see he also has like 9 minus 3, and he have like 6 instead of another
Yeah.
8.
Yeah.
So
Yeah.
I was thinking maybe we will find out, but I was trying to make some sense taking that. So maybe he only uses this the top and the bottom as borders, and in between do a normal convolution, so you get those strange shapes. It's not like you do normal convolution and escape on the margin up top and bottom, and you can get the strange output.
Yeah, that's a good point. Yeah, your name shows as TYOC, but what's your name actually? Because I've seen you in here lots of times.
David.
David. Okay, so David, that's a really good point. I hadn't noticed that if you look at this part of the feature map comes from these 2 words, but this part of the feature map comes from the 2 words behind it. And I'm thinking that one of these is the the predetermined word vectors, and the other is the word vectors that got determined. Yeah, static and non-static channels. So static means predetermined word vectors from the word to vec model. So one of these is that, and the one behind it is the non-static. That is, we're solving for them. I had not noticed that one feature is coming from this one, from both. So in some way, he's combining these 2 things to get the feature map. I think that each pixel here has contributions from both these 2 words and these 2 words, averaging them together perhaps. But
we will find out.
yeah, and he talks about it. I think in further on in the paper we'll see what he says. But the math isn't really off-putting. You know, every time you see math, you kind of want to run the other way sometimes, but it's not really that off-putting. X1 through N is basically just saying we're going to take that we have words that we have a concatenation of a bunch of words together. Let's go back up a little bit and see. So the model architecture, let xi in rk. Rk means vectors of length k-dimensional word vectors. These are the embedding. This is the embedding space. And xi is the ith word, and it's represented by a k-dimensional word vector, right? So, and it corresponds to the ith word in the sentence. A sentence of length n, and he talks about padding, is represented as x1 through n. This is not Pythonic indexing, but we understand what he means. The indexes go from 1 to n, and he's concatenating all of these word vectors together, right? And the concatenation could be n to n, but you can see that it's not. It's actually concatenated in the sense that we're stacking the words, right? So each of these vectors, x1, x2, xn, is a vector of length, 300 or k. Well, let's just say k. And in this case, it just shows k equals 6. But you get the idea. Each word vector is an embedding vector of dimension k. Okay, and then if you want to take a sub part of the sentence, you can go xi to I plus j. That means the words from the j words from I to I plus j. Is that j words, or let's see, 5. Yeah, I think it's j words. no, it would be 0. It would be j plus 1, wouldn't it? Yeah, I to I plus j would give you j plus 1 words. Yeah, and that's what he says here. The words from xi up to j plus I. So you can see that there's j plus 1 words here. A convolution involves a filter w. Remember, I was telling you the filter for a convolution is actually 2 dimensions. And the length of the filter is k, and that is the number of columns is k. It's a matrix of k columns and h rows, where h is the length of the convolution. So if h is 2, then it's going to be 2 by k, right? And it's applied to a window of h words, that is, in this case, h could be 2 or 3 or 5 or whatever, to produce a new feature. So for example, a feature ci is generated from a window of words. That's the words in the receptive field of the of the convolution, and it's gotten by taking the convolution. Let's see. Yeah, so you have a bias, you have a nonlinear function, which is like a ReLU. In this case, he says, well, he talks about hyperbolic tangents. And you produce the feature map. W is the convolution, is the convolution weights, and that's what he talks about here. So you multiply the convolution filter by the range, and then you add a bias vector, and then you follow it by a ReLU. And then that's the output of that is called the feature map. Okay, and we saw the schematic diagram for that, where it was up here. So this is the feature map that he's talking about. Then he takes, okay, so he says, okay, that's how you extract one feature from one filter. Then he says, the model uses multiple filters with varying window sizes. So, a window size of 2 means that it's looking at bigrams. If a window size is 3, it's looking at trigrams, and so on. That is 2 consecutive words or 3 consecutive words, and it runs through the whole sentence, capturing relationships between consecutive words. Okay, so there's the feature maps. These features form the penultimate layer. Penultimate means like second to the last, and are passed to a fully connected softmax layer, whose output is the probability distribution over labels. And we saw that here. The output of the softmax layer would be probabilities for these 2 labels in this case, or there could be 5 labels, or there could be 10 labels, whatever. And then he mentioned, okay, these features. He didn't talk. Oh, then he talks about the pooling. Okay, so he basically explains what the pooling layer is doing. It's capturing the maximum value of the of that feature map. Maximum value, and then you define a new feature corresponding to that maximum value. Maximum value of the feature corresponding to this particular filter. The idea is to capture the most important feature, the one with the highest value. So that's really easy to understand, right? You're just looking for the most important feature. And the other thing about this pooling scheme is that it naturally deals with variable sentence length. So you can look at this and say, well, what about a different sentence length? If you have sentences of different lengths, they'll give rise to feature maps of different lengths. And so how do you compare? You need a process that gives you the same output, the same dimensional output for a given input. But when you do max pooling, you naturally reduce everything to the one feature map that has the number of filters in it, that has the length of the number of filters. So here we've used 4 different filters, and so we get an output vector of length 4. It is completely independent of the length of the input vector, which is the sentence, right? And then finally we do a softmax and we make our classification. So it's a very simple architecture. I mean, it's really great for us because we're sort of pedestrians in this field, and we don't understand really complex things yet. But this is a really simple architecture for people to understand who are just starting to look at this stuff. So it's a really great paper for us to look at. And then he talks about so he didn't invent max pooling, but he just used it as, he basically used it as one of the ways to make this architecture better. So he's basically taking Lego pieces that already existed in the literature. He wasn't the first one to use convolutions on neural networks. He wasn't the first one to use max pooling. He wasn't the first one to use dropout. But he basically adopted all of these pieces and built a really nice model with them. So then we talked about dropout, and that's what he uses for regularization. And then he implements another piece that he found in the literature. So there's two ways that he regularizes. One is by employing dropout. We've already seen that. And the second thing where he has a constraint on the L2 norms, where the maximum value of the L2 norm, if it's bigger than, in his case, 3, then he sets it equal to 3. So this is the way he prevents gradient explosions, right? Exploding gradients, I guess. If the L2 norm of the weight vectors exceeds 3, he just clamps it to 3 and prevents it from being able to from running away. Okay, the last layer then, you have M filters. So there it is. The last layer, Z, is these is this feature map with M elements in it. And then you apply a linear, instead of using the linear layer, he says you apply dropout, where instead of you multiply this this filter, instead of by Z processed by this R, where R is the masking vector of Bernoulli random variables, right? So if the Bernoulli random variable is 0, that knocks out this dimension, right? Or makes it 0. Gradients are backpropagated only through the unmasked units. That makes sense. At test time, we mentioned this, the learned weight vectors are scaled by P, so that you get the same, so that you're comparing apples to apples from what you trained on to what you're predicting. We additionally, this is what I mentioned, we additionally constrain the L2 norms by rescaling W to have norm of S, where S in this case is 3, whenever the norm is bigger than S after a gradient descent step. So yeah. So that's the whole thing right there. That's the whole architecture, and we're only on page 2 of the paper, right? So 2 pages to describe his architecture, and the rest of it is all describing some of the hyperparameters that he used and some of the other features, right? So we can go through this. This is an interesting part because in a lot of these papers you see all these acronyms for which data sets are being processed, in other words, what the models are doing what. Well, when you compare all the results in the results table, and here are the data sets that are being processed. A movie review data set with 1 sentence per review. This is 2014, right? Now we have the IMDb data set, which has, each review consists of multiple sentences, but back in these days, this data set was what they had available. SST1, Stanford Sentiment Tree Bank. It's also extended from this movie review data, but providing train test deb splits and fine-grained labels. So in other words, instead of just plus and minus, it has 5 different labels. Very positive, positive, neutral, negative, and very negative. Socher, the guy from Stanford, who's collaborating with Manning on a lot of these papers, created that, I guess. And then SS2, same as SST1, but with neutral reviews removed. and binary labels. So this is what I was telling you. You take the neutral reviews, since you know, it's hard to classify something that has that has 0, so you just remove it, remove all the neutral reviews, and then lump together the positive and very positive to be the plus class, and the negative and very negative to be the minus class. So now you have a you've changed this to a 2-level problem, a 2-level classifier. Okay, and then here is another data set, subjectivity data set, where the task is to classify a sentence as either being subjective or objective. In the sense of subjective meaning an opinion, objective meaning a fact. That's what I would think that means. And then this one is TREC, classifying a question into 6 question types. So this is kind of like, kind of related to the question answering problem that he's having everybody do in this class. And it's old, from 2002. So here you just have to classify whether the question is about a person, about a location, about a number, about numeric information, and altogether 6 classes. And then here's the customer reviews. This sort of predates the Amazon customer review database, but it was already around in 2004. Customer reviews of various products. The task is to predict positive or negative reviews. And then I guess it has more information, let's see, about these. But the point is we can understand these data sets, what they are. They're basically 2-way and 6-way classifiers, 2-way, 5-way, and 6-way classifiers. That's what they all end up being classifiers into a small number of categories. He talks about this, getting the word-to-vec vectors, and the reason why they're so good is because they were trained on 100 billion words from Google News. The vectors have dimensionality of 300, and were contained using the bag of words, the CBOW, continuous bag of words that we've studied earlier in the lectures. Words not present in the set of pre-trained words are initialized randomly. So let's see, the set of pre-trained words are initialized randomly. Okay. Not sure what he means by that. Remember, he uses 2 possibilities. One is to use these pre-trained vectors, word vectors, but other is to train the word vectors, start with random word vectors and train them in the process of solving the model. So here's he talks about the variants of his model. CNN RAND, the baseline model, where all the words are randomly initialized and then modified during training. So this is where he doesn't use word-to-vec. He just solves for all the embeddings by starting out with randomly initializing them to 300 length, to vectors of length 300, and then running them through the neural network and solving for them through backpropagation. CNN static is the one we talked about, where you use pre-trained word vectors from word-to-vec. All words, including the unknown ones, are kept static, and only other parameters of the model are learned. So this is where the sentence from before here, when he says that words that are not that are not in the model. So if you come across a word in your sentence that isn't in the word-to-vec data set, then you just randomly initialize it and leave it. Don't even try to solve for it. Okay, so that's the CNN static. Randomly initialized and modeled. CNN non-static, same as above, but the pre-trained vectors are fine-tuned. Okay, so you start out with the pre-trained vectors and then you let it fine-tune. And then this is the one we were talking about, the CNN multi-channel, a model with 2 sets of word vectors. Each set of vectors is treated as a channel, and each filter is applied to both channels. And this is what the picture was showing. Gradients are backpropagated. This is the part we didn't see. Gradients are backpropagated only through one of the, only through one of the channels, because the other one is static, right? The other one is static. So the model fine-tunes one set of vectors while keeping the other static. And let's see, both both channels are initialized with word2vec, so not randomly. So one channel is initialized with word2vec and stays fixed. And on the other channel, you initialize with word2vec, and then you train them on the network to fine tune. Okay, in order to see, okay. Results and discussion. The main thing, I think we have to stop pretty soon, so I'm not going to go too much longer. He talks about initial and multi-channel models. His idea for the multi-channel architecture is to prevent overfitting. The results are mixed and further work on. So he didn't find much of a benefit from the multi-channel model. So here's a comparison for finding the most similar words, its result. Finding the most similar words in the final embeddings. So if you have a static channel, that means that you're just using the pre-trained word2vecs. The most similar words to bad in the movie are in the word2vec model: good, terrible, horrible, and lousy. But when you fine tune them, then changes a bit. You know, terrible and horrible and lousy are still there, but now you have stupid, which tends to occur in movie reviews, right? So anyway, that's interesting. Static versus non-static. We can look at probably the thing we should do now is look at the conclusion. Present work we have described experiments with convolutional neural networks built on top of word2vec. And here's the kicker. He says, despite little tuning of hyperparameters, a simple CNN with one layer of convolution performs remarkably well. Our results add to the well-established evidence that unsupervised pre-training of word vectors is an important ingredient for deep learning and for NLP. So that means he found that pre-training those word vectors was necessary to get really good results. We should look at the table really quickly before we leave to go to Srinivas's next meeting. Let's see, look at the table. Yeah. So remember, this is the one. Let's see. MPQA. I don't remember seeing what MPQA is. Anyway, the point is that here's his models, the CNN models, and of these 7 data sets, of these 7 problems that he addressed, he got state-of-the-art results in 4 of them. So this is like a huge blow to all of the classical NLP scientists who had spent their whole lives learning about parsing and all kinds of technical linguistics and language processing stuff. And here comes this newcomer just jumping in and getting results just as good as theirs, or only slightly less good. In the case of some of these tests, like here's the 3 tests that he didn't do as well in, he did almost as well. Remember, this is high score is better, I guess. So they beat him. You know, state of the art was better, but his best model was 48, and state of the art was 48.7. So he didn't do too badly. Here he beat the state of the art. Here he came. So the state of the art is 93.6, and he got 93.4 with his best model. So he didn't, even when they beat him, they didn't beat him by much. Here he got 93.6, his best model, and they had 95.0, so he's almost as good. And here he just blew them away in this category, in this test. And again, in this test, this is significantly higher score than state of the art. So the moral of this story is, you know, this is a very simple architecture, and it's very powerful because it, without any domain knowledge at all, you can come in and capture state-of-the-art honors in 4 out of 7 classical tests. So I think this is a really important paper to look at. I didn't have time to go through the second paper that I wanted to, but and that paper was the one referred to. I noticed that I don't have it here. That paper was the one referred to in this in these notes. It's this one, the Kaltenbrenner et al. Paper, where he talks about narrow and wide networks. This is narrow and wide convolutions. Narrow is what we were talking about without any zero padding, And wide convolutions is when you allow zero padding. That's the only difference. Anyway, I'm going to leave now so that people can go to Srinivas's meeting. And let me just quickly look at the chat. See if somebody says paper was before transfer learning, right? It was both original and pre-trained. Interesting. It looks like he's doing transfer learning, right? Doesn't this look like transfer learning? This paper is 2014. The transfer learning in vision problems was already done by this time. I think it was done in 2012. So it wasn't before transfer learning, but maybe it's one of the early transfer learning papers in NLPs. Okay, so that's it for today.